Let's now look at part 1.4 of lab 21. So one input of our NAND gate is just hardwired to plus 5 volts. The other input is connected to a signal generator, 5 volts peak to peak, 2.5 volt offset triangle wave. So it's going back and forth between 0 volts and 5 volts. This says a kilohertz. I'm starting off at a hertz so you can see directly with your eye. And then we still have our 100 ohm resistor and the diode. So you can see over here, the LED is blinking on and off at 1 hertz. And what's connected? So this junk on the left side is just left over from the earlier parts of part 1, the push buttons. These are the 2 ground connections. This is the plus 5 connection in red. Then in yellow, I have signal generator number 1. And then orange is channel 1 of the oscilloscope, and blue is channel 2 of the oscilloscope. So yellow and orange are both going into pin 2 of the CMOS NAND gate, and blue is going into pin 3. So over here, actually maybe, I have to go back a couple pages, so maybe I won't do that. Maybe I will do that. Okay, yeah. So this is wired straight to 5 volts. This has this yellow signal generator input. It also has the orange scope probe. And this has the blue scope probe, and it's also going through a 100 ohm resistor to the LED to ground. And of course, this is plus 5 volts, and this is ground. Okay, back to the lab. Okay, my signal generator is just doing 1 hertz here. And then if we go over to scope, this is kind of fun. You can see the input in yellow going up and down between 0 and 5 volts, and you can see the output of the CMOS NAND gate, which is functioning as an inverter. And then I guess we could make the time scale be something like 200 milliseconds per division, and you can see that's kind of cool. Here, let's stop this. So you can see that at 0 volts, you know, the inverse of 0 volts is 5 volts, and then it gets up around the threshold region, and somewhere around the threshold region, and it switches down. And then it stays in that low state, and then you get back and cross the threshold in the other direction. So what the lab wants us to do is to see what happens when we switch much more quickly. So let's go to the waveform generator, and let's make this, well, Tom suggested 1 kilohertz at first, so let's try 1 kilohertz. Then we go back over here. Now we need a more, here, let's do like auto triggering, and let's do like regular repeated trigger, and we'll do, I don't know, 200 microseconds per division. Okay, fair enough. Now let's do this a little faster. So we'll go over wave gen, that was a kilohertz. Let's go up to 10 kilohertz. We'll go back over to scope. We'll go to 20 microseconds per channel. Okay. Then let's go back and try to go even a little faster. Here's 100 kilohertz. And then we'll go and make this 2 microseconds per division. Okay. And then, Oh, I see. What we're supposed to do is replace the triangle with a square. Okay, let's do that. So let's go over to wave gen, replace the triangle with a square, and then we'll go back over to scope. And the question is, how long does this thing take to transition? So let's zoom in a little more, and let's zoom in a little more. And well, see, the thing is, this oscilloscope has a pretty poor time precision. The one in the lab does a much better job. But it seems like, see, this is 10 nanoseconds per division now horizontally. So it seems like as the input goes from low up to high, it seems like there's a delay kind of on the order of 1 box, something on the order of 10 nanoseconds. It's actually, unfortunately, we don't have the precision really to tell in this graph what the propagation delay is because everything happens so slowly. Another thing that sort of slows things down, I think, is the presence of this resistor at the output. So if I just pull this resistor out, let's see, that makes things a little sharper, I think. Here, let me put the resistor back in and then take it out. Actually, it doesn't make too much of it. It would make a bigger difference on a real oscilloscope. Okay, so actually this is not very convincing, but I claim that the propagation delay from the input changing to the output changing should be on the order of 1 box here. I think in past years we've measured it to be something like 10 nanoseconds, and I think the data sheet says, well, less than 23 nanoseconds typical value is 9 nanoseconds. So that's a little bit disappointing. Anyway, actually one thing that's a little more clear though is if we back out to, let's say, 100 nanoseconds per division. See, this does look pretty decent. Like you see the input goes from low to high and the output goes from high to low. What you can't quite see though is how big is the delay. See, when we went back actually to Mr. Triangle Wave, here's Mr. Triangle Wave, and then we go back to Mr. Scope, and let's go out to whatever some appropriate time scale is. You can see that the transition happens somewhere around 2.5 volts here. Actually, so in that case, here, let's make the offset be minus 2.5 volts. Let's make this offset be minus 2.5 volts. Okay, yeah, so now you see the transition happens somewhere around the middle of the screen. And then now let's go back to Mr. Square Wave, wave gen, square, and then we'll go back to Mr. Scope. Okay, so then the question is, if we zoom in on this in the time base, can we see the delay right around this level? And seems like, maybe you can claim the delay is roughly 1 box, but again, this scope is not a high enough time resolution really to say. So, but the right answer is about 10 nanoseconds. I think you could see that with a real scope. Okay. Here, wait, just for fun, I'm gonna go back to my 1 hertz and I'll go back to 1 hertz and I'll put the, oh well, no, I pulled out the resistor, so you don't see the LED blinking. Okay, bummer. End of the video is kind of a bummer.